Okay, this video is going to deal with geometric sequences. We've had a video on sequences in general, and then our previous video was 12.2, that was arithmetic sequences. Now we have section 12.3, geometric sequences. So what do we need to know about geometric sequences? First of all, they're sequences. So that means they're functions, right? Sequences are just functions. We don't want to overcomplicate sequences. Remember, sequences are functions that have as their domain the positive integers, just 1, 2, 3, 4, 5, 6, etc. So we're going to begin with, in the geometric sequences, we're going to begin with our first learning objective. And our first learning objective says we want to determine if a sequence is geometric. Determine if a sequence is geometric. Now, in the previous section, we had to learn how to determine if a sequence was arithmetic. Now we have to determine if a sequence is geometric. Often on a test, we'll get a question that'll say, is the following sequence arithmetic, geometric, or neither? And so that question would allow us the opportunity to test this learning objective and the learning objective from the previous section. So where are we going to begin? We're going to begin with the definition. That's exactly what we did with the arithmetic sequences. We began with the definition. So it says a geometric sequence may be defined recursively, just like before, as, and it begins very similarly to our arithmetic sequence. We say the first term is A. That's our starting term. And then from there, we say, right, our first term is A. And then we say, if we take the ratio, not the difference. Last time we were doing a difference. Arithmetic was a difference. Here we're taking a ratio. If we take the ratio of the nth term to the term that comes immediately before it, we should get R. Now, there's another way we could write this, right? There's a second way we could write this, just like there was with the arithmetic. We could say, instead of saying this, we could say, all right, my first term is A, right? My first term is A, and then my nth term, right? We're going to do a little algebra over here. We're going to move this up here to this side. My nth term is R times the term that came before, n minus 1. Now, the difference between geometric and arithmetic was about adding a common difference, Here, we're multiplying, right? We're multiplying. And then the definition goes on and says where A sub 1 equals A and R, which cannot be 0, are real numbers, so they have to be real numbers, and R cannot be 0. And we'll see an explanation of that as we start to work through some of the problems that will start to make sense. And now we finish this definition just like we finished the definition in arithmetic sequences. We go ahead and say the number A1 is the first term And the non-zero number, right? We said it couldn't be 0. The non-zero number R is called the common ratio. For arithmetic, we call D the common difference. Difference because we restated this in terms of a sub n minus a sub n minus 1. But here it's a sub n divided by a sub n minus 1. Hence, we form a ratio, so R is called the common ratio. Right? So what do the terms look like here? Well, our first term, right? Our first term is going to be A1, right? A1. And then what does our next term look like? Well, our next term, A sub 2, is going to be that first term times R. And then our next term, A sub 3, it's going to be the second term, right? It's going to be the second term, A sub 3. This is a 3, so that's 3 minus 1. That's going to be the second term times R. But what do we know the second term is, right? We're going to go back here and we're going to look. The second term is A1 times R. So that's going to be A1 times R times another R, or A1 R squared. So the third term has an R squared. The second term has an R to the first, as it turns out. The first term has an R to the 0. So we get the idea that perhaps this is going to have a pattern just like, not just like as in identical to, but in behavior, a pattern that's similar to the behavior of the arithmetic sequence. So what is a problem that we're asked to work on, right? What does one of our questions looks like? What's an example of a problem? Well, they give us something and they say, tell me, is this arithmetic or is this not arithmetic? So, sorry, geometric. I apologize for that. So, what would a question like that? What would a question look like that started out like this? Well, they could give us a problem, that looks something like this, like, 2, and then 6, and then 18, and then 54, and then 162, and on and on and on. Now, is this geometric? Well, we can take a look. Remember now, geometric, it's about a multiplication by R. It's not an adding. It's not what do I add to 2 to get 6. It's what do I multiply 2 by to get 6. Well, I multiply by 3. What do I multiply 6 by to get 18? Well, I multiply by 3. What's 18 times 3? Turns out to be 54. And 54 times 3 turns out to be 162. So this is geometric because it has a common ratio of 3. A here is going to be 2, right? My first term is 2, and my common ratio is going to be 3. And again, if you're thinking this looks familiar, it's because you're correct. You did this in Algebra 2 last year. Just exactly the same thing we're doing now. Okay? What happens if they write it, though, in terms of, instead of writing the terms like this, what happens if they write something like, something like this? A sub n equals, say they make it 3 to the minus n. Now, our job is to determine if this is geometric, right? Geometric. So what are we going to do? Well, we're going to be asked, what we probably are not going to do is make a list, right? We will make a list. We're going to do that. I'm going to write that right here. We're going to make a list of the first let's say 4 terms. So what do we get? What's a sub 1 going to be? Well, a sub 1 is going to be 3 to the negative 1. Okay, that's 1/3, isn't it? What about a sub 2? Well, a sub 2 is going to be 3 to the negative 2. That's going to be 1 over 3 squared. That's going to be 1 over 9. What about a sub 3? Well, a sub 3 is going to be 3 to the negative 3. That's going to be 1 over 3 cubed. That's going to be 1 over 27. And finally, we said we're going to do the first 4 terms, so what's a sub 4? That's going to be 3 to the negative 4. That's 1 over 3 to the 4th, and that's 1 over 81. So, if we were in an Algebra 2 class, one of the ways we could answer this is we could list a few terms and we could say, okay, what do we do to go from here to here? And we say, well, we multiply by 1 over 3. That's correct. What'd you do to go from here to here? Well, I multiplied by 1 over 3. Also correct. What did you do to go from here to here? I multiplied by 1 over 3. Again, also correct. And if we were in an Algebra 2 class, perhaps our teacher would say, great job, you proved it's geometric. But we're not in Algebra 2, we're in pre-calc. We want to go back and we want to do this. This is what we want to do. We want to show not that the third term divided by the second term is 1/3. We want to show the nth term divided by the n minus 1 term. We want to compute, right? We want to compute the nth term divided by the n minus first term. Now, how are we going to do that? Well, we're going to use our general term here, and we're going to say the nth term is 3 to the minus n. Now, what about the n minus first term? Well, n minus 1, right? This is n minus 1, so this is going to be n minus 1. So this is going to be divided by 3 to the minus n minus 1. Okay? Now, what do we know? We know negative exponents go on the bottom. When they're in the numerator, they move to the denominator. When they're in the denominator, they move to the numerator. So what does this look like? This moves up, right? This moves up and becomes 3 to the n minus 1. This moves down, that becomes 3 to the n. All right, now we're going to find out how well we did in Algebra 2. That's what we're going to find out right now. Because what is this? Well, this is 3 to the n times 3 to the minus 1. That's one of our rules, right? We have that rule that says a to the n times a to the m is a to the n plus m. Well, in this case, we have n minus m, so we're going this direction. We're very, very used to going this way. This is the way we're typically used to using this rule, but now we're going backwards. We're breaking it apart. And so this is n, we can think of it this way, n plus negative 1, right? So it would be a cubed times a to the negative 1. In this case, our a is 3. Now, what do we have on the bottom? We have 3 to the n. Well, this 3 to the n and this 3 to the n cancel, and we're left with 3 to the negative 1, which is 1 over 3. And there we go. We got our common ratio. And because we got our common ratio, we would conclude that that series is geometric. Okay? This is going to be a trick we use a lot. This idea of what does 3 to the n minus 2 mean? That means it's 3 to the n times 3 to the negative 2. We're going to have to write that on our notes and not forget it. We're going to make use of that quite a bit. All right. So, what's our second learning objective, right? So let's clean the whiteboard off. all this off. What's our next learning objective, right? So this is learning objective number 2. And learning objective number 2 says, find a formula for the geometric sequence. So this is learning objective number 2, and we want to find a formula for a geometric sequence. Okay, we want to find a formula for a geometric sequence. Now, how are we going to do that? Well, we're going to make a list. We know our first term, A1, we know that's A. Right? What's our next term? What's our second term? Well, remember what our second term is by definition, right? Our second term is R times our first term. But we know our first term is A. So our second term is R times A. Now, what's going to be our next term? Now typically we write these with the A in the front. So I'm going to rewrite it like that. What's our third term? Well, our third term is R times our second term, isn't it? Because each term we find by, instead of adding D like we did for arithmetic, we multiply by R, right? Geometric, we multiply by R. Now we know what that is. That's R times AR. So that's AR. That's not where it goes, is it? That's AR squared, isn't it? Isn't that what that is? Now, what's our fourth term? I think we're starting to see a pattern here. What's our fourth term? That's going to be R times our third term. That's going to be R. And our third term is AR squared. So that's going to be A times R cubed. So when we have a 2, our power on R was 1. When we have a 3 for A sub 3, our power is 2. When we have a power a 4 for A sub 4, our power is 3. I think we can predict if we want the nth term, we're still going to have an A, we're still going to have an R, but now our power, if our power is 4, we get a 3. 3, we get a 2. 2, we get a 1. N minus 1. Okay. So this right here is the formula for the nth term of a geometric sequence A sub n, right? Now remember, that's just a function. That's just a function whose first term is A. And whose comma ratio is R. Right? That's our formula. And perhaps if you remember anything from Algebra 2 about geometric sequences, perhaps that looks familiar to you, right? Now, remember, we have a rule here, right? We have a rule about R. R cannot be 0. Why did we say R couldn't be 0? Previously, I said we'd come back and we'd look at that. So let's take a look at it now. If R is 0, then every term after our first term is going to be 0. And that's not going to be a geometric sequence. A geometric sequence says we have to be able to determine this term by multiplying by R. So if all the terms are 0, that's not going to be geometric. We've settled on a definition where R can't be 0. So since R can't be 0, we can't say all of the following terms are going to be 0, therefore this is geometric. Right? That's just the definition we've settled on. Now, what are we going to do with this? Right? What does a homework problem look like that uses this? Well, I think you're going to see some similarities between this section and what we did in the previous section, right? What does a problem look like? Well, they may ask us to do an example like this, right? They could say it like this. They could say, well, A1, right? A1 is 6, and R is -2, right? And it could say from there, find a sub 6, the 6th term, right? And a sub n, the general term. So this is what a typical homework problem could look like. Now, how are we going to find the 6th term? Well, what we don't want to do is make a list. We don't want to do that, right? We want to avoid that, because if we're going to make a list, our teacher is going to ask us to find the 60th term, and it's going to take the whole test to do one problem. So how do we get around that? Well, we have our formula right here. We're going to use this. We know what the 6th term is. We know the 6th term, right? N is 6. The 6th term is A. We'll plug that in a second. R to the 6 minus 1. That's going to be A times R to the 5th. Now, if we plug everybody in here, we know A, right? We know A. A is 6, so we'll put that in. We know R. R is -2 to the 5th power. Now we're going to do some arithmetic here, right? We're going to do some arithmetic. -2 to the 5th. Well, that's 5 negatives. So that answer is going to be negative because we have an odd number of negatives. 2 to the 5th, right? 2 to the 5th is 16. So this is going to be negative from here, and then it's going to be 6 times 16. And again, you've seen me do this many times. I'm going to work this out as 6 times 10 plus 6. The distributive property helps me do my multiplication quickly. So what do I have here? I have negative. 6 times 10 is 60. 6 times 6 is 36. So we get -96. So our 6th term is -96. Now, they didn't want just that, though. They wanted the nth term. Now, we know what the nth term is. The formula, again, is right here. It's A times R to the n minus 1. Now, we're doing this for n. We don't have a value. Here we had a value 6. Here we just have n. But we do know A still. A is still 6. And we know who R is. R is -2 to the n minus 1. Okay. So that would be an expression for our nth term. Now, that's what a problem dealing with learning objective 2 typically looks like, all right? So I'm going to erase this. You'll see plenty of homework problems that look just like this. And there are examples in your book as well that you can follow. You know, this doesn't have to be the place where you go to get all your answers. Your textbook has plenty of wonderful examples, so make sure you read those as you're learning this material. So now we're on to learning objective 3. And what does it say? It says we want to find the sum of a geometric sequence. We want to find the sum of a geometric sequence, okay? Just the sum of the first n terms, right? The first n terms. So where are we going to go to find that? Well, let's write that down. Find the sum geometric sequence, right? And we only want to work with n terms here, n terms. We're going to, in a few minutes, we're going to find a formula to find the sum of an infinite number of terms of a geometric sequence. But right now, we're just working with n terms, right? N terms. So where are we going to go to find this? All right, so here's where we're going to start. We're going to start with the fact that what does our sum of the first n terms look like? And if you're thinking to yourself, oh my goodness, we did this a few minutes ago. We did, well, a few minutes ago in my time, but on the previous video, we did this, and we developed the formula for arithmetic sequences. We're going to do the same thing today. We're going to develop the formula here for geometric sequences. So what does this look like? It looks like a1, my first term, plus my second term is a1 times r, isn't it? What's my third term? Well, my third term is a1 times r squared, right? And then I have a1 times r to the third. And this keeps going, doesn't it? Just like the last time, it keeps going. We know what our last term is going to be, right? Since we're looking for n of these, our last term is a1 times r to the n minus 1. That's what our formula said. If we want this first n terms, this is our n term. The term that comes before that one is a1 r to the n minus 2. All right? Now, last time, we just wrote it the other way backwards. We're not going to do that this time. This time, we're going to develop, the development takes a bit of a different approach. We're going to multiply this by r. Okay, we're going to ask ourselves, what does this look like if I multiply it by r? Well, what would this look like? This would look like a1 times r, wouldn't it? Now, I'll tell you what I'm going to do, and this is going to probably be a bit of a hint. I'm going to start by writing that right here. All right, so I took this, I multiplied by r, a1 times r. Now I have to multiply a1r by r, so that's going to be a1r squared. I have to multiply a1r squared by r, that's going to be a1r cubed. I have to multiply a1r cubed by r, that means I'm going to get a1r to the fourth. Now, I have to multiply a1r to the n minus 2 by r, that means I'm going to get a1r to the n minus 1. And I have to multiply a1r n minus 1 by r, that's going to give me a1r to the n. Now let's just talk about that for a second. Let's take a look and see if we can justify for ourselves why that works. We're taking r times a1 times r to the n minus 1. Right? This is a little exercise in exponents. That's going to be a1 r to the first r to the n minus 1. If you just allow me to reorder them. But what do we do if we have somebody to a power times the same base to a different power? We add the bases together, right? Isn't that what we do? So we get a1r, and our new power is going to be n minus 1 plus that 1 right there. Well, if we look at that, that certainly turns out to be this, right here. Now, why did we do that? Right? What was we did that because the book says, hey, if you want to develop a formula, this is your approach. I'm not so sure that we would have thought of that on our own, but that's the approach. Now, what are we going to do? We're going to subtract these. What do I mean by that? I mean, we're going to multiply every one of these by negative 1. Okay? Now we're going to add straight down. We're going to add straight down. Look what happens over here. Over here we have s sub n minus r s sub n, because we just add those up. This one's negative. What happens on this side when we add? Well, there's nobody under the a1, so that comes straight down. But look at this. We have a1r minus a1r. That's going to be 0. Here we have a1r squared minus a1r squared. That's going to be 0. Here we have a1r cubed minus a1r cubed. Look at this. It's not a, it's 0. Now there's going to be an a1r to the 4th up here. We didn't write all the terms. It's going to cancel this one. All we're going to get is this endless string of zeros. This one's going to be canceling 1 down here. That's also going to be a 0. This a1r to the n minus 1. Here's a minus a1r. That's also going to be 0. And what happens down here? Well, down here, this comes down because there's no term up here to cancel it. Now, if we rewrite this, right, we can factor in s sub n out right here. So we get s sub n times, if we take an s sub n out of s sub n, that's 1. S sub n divided into r times s sub n gives us an r. And who's on this side? A1, right? A1 minus, oh, I forgot the 1 right here, didn't I? A1 r to the n. Now, remember what we were looking for? We're looking for the sum. What do they add up to? Well, they add up to this. We can simplify this. S sub n is equal to a1 minus a1 r to the n, all divided by 1 minus r. I just divide this down here. Now that gets us this formula right here. a1 times 1 minus r to the n divided by 1 minus r. This is our formula for the sum of the first n terms of a geometric sequence. If we sum up the first n terms, this is the formula we're going to use. a1 times 1 minus r to the n divided by 1 minus r. Now, remember, we had already previously mentioned r can't be 0. And if you look at this formula, you'll notice it doesn't work if r is 1. So we have to eliminate 1 and 0 from our values of r. Now, if you're wondering, do you have to remember where this comes from? Not unless you're in my class, right? Not unless you're in my class. In my class, yes, you have to remember this. I feel like it's important to remember this because if we sit down to take the test and we forget the formula, well, now we know where to go get the formula. All right? So what does a problem look like that would require us to use this, right? What do they want us to do? Well, they give us a problem. Here, we'll do an example. Right? We'll do an example. So they give us something like this. Let's just pick a problem here. They give us sigma, right? K equals 1 to n. And it's 4 times 3 to the k minus 1. Right? Now, we could write down the first couple of terms if you wanted to. If k is 1, right? If k is 1, what does this look like when k is 1? We get 4 times, and we get 3. K is 1, so that would be 1 minus 1. That would be 3 to the 0. Plus, what's our next term look like? Well, our next term, k is 2, right? So it's going to be 4 times. K is 2, so that's going to be 2 minus 1. That's going to be 3 to the first, isn't it? Plus, what's our next term going to be? Well, our next term, k is going to be 3. 1, 2, 3. K is going to be 3, so that's going to be 4 times 3 minus 1, that's 3 squared. And now our last term, right? Our last term, what's our last term going to be? Well, it's going to be 4, right? Times 3. Now for our last term, k isn't 1, k isn't 2, k isn't 3. K is actually n, so it's going to be n minus 1. So that's a list of what they want us to sum up. Now we can't add those up. We don't have a calculator that will allow us to calculate this. We can't sit down and add all these things together and say my answer is. So what do they expect us to do then when they said sum, right? Sum, that's our summation sum. Well, they expect us to use the formula that's right here. So we have to find A, our first term. Our first term, well, what is our first term? 3 to the 0 is 1 times 4. So our first term is 4. Then we have to find our common ratio, don't we? What did we do, right? What did we multiply by? This term to this term. What did we do? We multiplied by 3, didn't we? We have 3 to the 0, we have 3 to the first. We multiplied by a 3. What did we do to go from this term to this term? We have 3 to the first, we have 3 to the second, we multiplied by 3. So our common ratio, right, our common ratio here is going to be 3. 3 is our common ratio. Now, what do they want me to do? They want me to write my sum. So I have to write this formula. This is the best I can do. So my sum here, right, my sum for the first n terms, because we're not going to 3 or 6 or 12, we're going to n, is going to be A is 4, times 1 minus r, right, 1 minus, my r is 3. Now the power that goes on this is wherever I'm stopping, so I'm stopping at n, so I have to put an n there. Now I don't know what that is, I can't calculate that on my TI-30 or anything else. What goes on the bottom? I have 1 minus 3. Now, can we simplify this? Well, yes, we can. We have 4. We have 1 minus 3 to the n. And on the bottom, we have negative 2. Well, negative 2 divides into 4. That gets us negative 2. And we get 1 minus 3 to the n. Now, that's our answer, right? This is our answer. Unlike some of the problems where we are asked to sum them up, we couldn't come to a definitive numerical value because they didn't tell me where to stop. They left my stopping point as a variable. Now, what does that do for us? Well, if I ask you to stop at 5, you don't have to redo the work, do you? If I ask you, say I went back to the problem over here and I said, hey, you know what? I don't want you to stop at n. I want you to stop at 5. Well, you know the answer. You can come over here and plug in 5. Just cross this out and put in a 5. If I ask you to stop at 51, you put a 51 there. So the formula might be more useful than the answer itself. The answer is only going to work when there's a 5, but we found it for n. All right? So that's our learning objective number 3. We want to find the sum. We want to find the sum of a geometric sequence, but we only want to do that for a finite sum, in terms, okay? All this work about to disappear. Okay, that gets us to learning objective number 4, right? Learning objective number 4. Learning objective number 4 what does it say? It says determine whether, determine, so we got to make a decision whether a geometric sequence. Well, hold on a sec. I'm going to change this word, and we'll talk about that just in a second. I'm going to change this to a geometric series. Converges or diverges? Now, we have a lot of words here that we're going to have a conversation about before we can go any further. All right? So we need to have a conversation about what do these words mean. Let's start with series. Series just means the sum of a sequence. So a series is just a sequence and we add all the terms together. Just like the last example where we added all the terms together. That's what a series is. All right, that's what a series is. Now we have this word converges, right? What does it mean if an infinite series converges? Well, an infinite series converges when its sum is a finite number. So if our sum turns out to be finite, now remember, we're adding up an infinite number of terms here, an infinite number of them. But if for some reason when we add up an infinite number of them, we get a finite number, we say it converges, right? We say it converges. However, if it does not converge, it diverges. All right. If it does not converge, the word we use to describe that is diverges, or we say it's a divergent series, a divergent series. All right. So, what does the sum of an infinite geometric series look like? Well, an infinite sum looks like this. It looks just like you think it looks. We take our first term, and then we have our next term, and then we have our next term, and we have our next term, and we have our, yeah, you get the idea. It goes on forever. It never stops. It doesn't end out here at n because n is infinity. We just add all of these up. Now this is where math starts to get a bit interesting. When we get to calculus next year, if you take a BC class, when you get to calculus 2, we get to study sequences and series. This is where math actually starts to become kind of fun. So, not that it's not fun now. I mean, obviously, this is the height of everybody's day. I mean, who'd rather be doing anything other than this? So, what does this look like, right? What does this look like? We could write this in our summation form if we wanted to. We could say, well, k is 1, right? We have a sub 1. We have r to the k minus 1. That's our formula. And instead of stopping at n, now we're going to stop at infinity. We're going to stop at infinity. Okay? So, I'm not going to develop this proof. I'm not going to take the time to do that. I'm going to give you the formula, right? I'm going to give you the formula that says this. The sum of an infinite number of terms of a geometric series. Right? An infinite number of terms. What does that equal? Well, it equals a, our first term, divided by 1 minus r. Now, don't get excited. That's not going to be necessarily the case every time. So we have to remember this, right? We have to remember this. If the absolute value of r is smaller than 1. Now, this means what? i.e., negative 1 is less than r is less than 1. If our common ratio is between negative 1 and 1, then we're going to get a sum. We're going to get a sum. So, if we just make something up, right? If we make something up, if we say a1 equals 1, and my common ratio is 1/2. 1/2 is clearly between negative 1 and 1. What does this look like, right? What does this sum up to? If we add up an infinite number, well, what is our first term? Our first term is 1, isn't it? Isn't our first term 1? What's our next term going to be? Well, our next term is going to be 1a times 1/2. My next term is going to be 1, which is a, times 1/2 squared. My next term is going to be 1, which is a, times 1/2 cubed. My next term is going to be 1, which is a, times 1/2 to the 4th. And I'm just going to keep going until time ceases to exist. Now, we can simplify this, right? We know that's 1. We know that's a half. This turns out to be a 4th, doesn't it? This turns out to be an 1/8. This turns out to be a 16th. Now, based on our theorem right here, right? Based on our theorem that's sitting right here, we know the sum of that. Despite the fact that there's an infinite number of terms, despite the fact that these never cease, they never stop, they're always positive, we know what this sums to. It sums to a divided by 1 minus our common ratio. That's 1 divided by 1/2, or 2. If you add this up until time ceases, you get all the way out here at infinity, you only get to 2. You only get to 2. That's it. The theorem says so. It's not going to lie to us. It's going to tell us right there the answer is 2. Now, there's some real interesting things, right, about this. What are some interesting things? Well, if we look at this piece, right, that goes off to infinity, 1 is right here, isn't it? Well, if I take 1 away from the other side, that means this green piece has to add up to 1. It adds up to 1. All of these numbers, the whole thing adds up to 2, and an infinite number of them, other than the first one, they only add up to 1. They only add up to 1. And we can keep playing this game, can't we? We can keep doing this. We could say, well, what do these numbers right here add up to? Well, we've taken away 1, we've taken away a half from 2. We only have a half left. So a 4th plus an 8th plus a 16th plus a 32nd plus a 64th, that only adds up to a half. It only adds up to a half. This is, like I said, this is where math starts to get interesting. Now, this geometric sequence adds up to 2. This is not geometric, right? But consider a sequence that looks like this. 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6 plus, I think you got the pattern here, 1 over 7 plus 1 over 8 plus, right? Look at this. Now, some of our numbers up here, right? Some of our numbers up here are down here. Like this one's up here in our list. This one's up there in our list. This one's up there in our list. This one's up there in our list. Now, the next one that's in our list is 1/16. This series right here, this series has a name. This is called the harmonic series. We study this in calculus. And I'm not going to prove it to you now, but I'm going to tell you right now, if you add this up, you get infinity. Look at the difference between those two. Sometimes we look at this and we say, okay, well, they're getting smaller, so it adds up to a number. No, that's not what does it. These are all getting smaller, and they add up to infinity. It has to be the case that it has to be geometric. Well, for a geometric series, it has to be geometric, and it has to have a common ratio below 1 or bigger than -1. Okay? So that will get you done with all O. Again, does this converge? I guess I didn't formally answer the question. We say this converges because, right? Well, we really knew it converged as soon as we wrote this down, right? As soon as we were told it was geometric and we wrote down R, it converges because it is geometric and the absolute value of R, which equals 1/2 for us, is less than 1. All right, so you're ready to go attack the homework in 12.3. All right, remember, this is your lesson. Your book is filled with examples. There's plenty of other videos out there for you to look at. So now you're prepared to answer the questions on 12.3.